Good afternoon, one and all. I am Ramachandra Mudali. My topic is chemically modified surface of silicon nanostructures to enhance hydrogen storage capabilities. First, hydrogen has enough potential to eradicate the barriers of conventional fuels, issues related to conventional fuels, with abundant availability and high interaction with hydrogen makes silicon as prominent candidate for hydrogen storage. And with chemical modification, they form silicon nanostructures which has enhanced surface area and roughness to store hydrogen. Here the isotherm curves of silicon nanostructures, which has different hysteresis loops, which indicates the fabrication of pores on the surface of silicon nanostructures. Here in experimentation, we have considered 6 different structures of two different resistivity. In high one, we have considered 0.01 ohm centimeter, and in lower one 0.001 ohm centimeter resistivity. And with porosilicon is formed by anodization, and silicon and porosilicon nanowires formed by metal assisted chemical etching. A high current density is provided to detach silicon nanostructures from the silicon surface. In result, here in this table, the 6 different silicon nanostructures which are considered. Here we can see due to chemical modification, this roughness and surface area enhanced in case of 6 structures, and the surface area increases about 437 meters square per gram, and the roughness enhanced to 602 nanometer. Due to prolonged chemical etching, this surface area enhances. Here we have considered only one structure, that is porosilicon, and this is the isotherm curve of porosilicon. Here we can see with increasing the relative pressure, the layer of gas molecules increases on the surface of pore wall, and at a particular relative pressure, the absorbed gas molecules condensed to transform a liquid-like phase, which is called capillary condensation. And due to capillary condensation, the desorption path is different from absorption, which leads to hysteresis loop. And here we can see the narrow hysteresis loop and parallel absorption-desorption curve indicates the formation of cylindrical type of pore on the structure, and that also indicates a uniform and homogeneous pore size distribution on the surface. The nuclear magnetic resonance spectroscopy shows the chemical hydride termination on the surface of silicon nanostructures. Here we can see the chemical shift in between -84 to -95. The higher intensity of chemical shift shows the maximum hydrogen related surface on the silicon nanostructures. In discussion, here we can see due to random parallel and perpendicular etching that forms different shape of pores, and also that leads to pore branching and pore interconnections on the surface. And the metal assisted chemical etching forms nanowires, and during air drying, the capillary force leads to a bunching of nanowires, and that bunching is maximum in case of porosilicon nanowire due to its enhanced surface area. The gas physisorption improves in nanopores due to the overlapping of attractive field from opposite pore wall, and this the chemical etching is more affected in case of lower resistivity, because lower resistivity silicon copper is more posed to this parallel and perpendicular type of etching. In this model, we have shown the hydrogen termination on the silicon nanostructures. Here we can see with only HF treatment, the hydrogen related species are terminated on silicon wafer. And after modifying the surface and with the increased surface area, the hydrogen termination also enhances on the surface. And with a proper activation of silicon nanostructures, we can go to a bulk storage of hydrogen. We can conclude here that with enhanced surface area and high potential as chemical hydride of silicon nanostructures, that gives a better platform for hydrogen storage. And with a uniform and homogeneous pore size distribution, the gas uptake capabilities also increases, and that also affects the cyclic life. The pore structures and pore behavior of silicon nanostructures are also responsible for the quality and quantity of gas and surface interactions. Here we can see in case of FTIR and TGTAC, the hydrogen desorption can possible with water rinsing and a thermal treatment of about 290 degrees centigrade. Here based on the morphological and fabrication parameters, a rank matrix is constructed where porous silicon stands prominently as a better candidate for her high potential hydrogen storage. And porous silicon nanowires with its nanopores on the surface and a high surface area and roughness, that acquires a second prominent position for hydrogen storage.